So what about can I see that? Do that instead? Makes it a lot easier to solve, right? What do you guys think? Does a factor of 2 matter? Not in this case. The exponential terms are going to outweigh that factor of 2. That's the only reason why I can throw away those pre-exponential factors as well, because those could easily vary by a factor of 2. I just don't care. So if I don't care about the factor of 2 and the pre-exponential factors, I can't turn around and suddenly care here. Now this does have the added benefit of I can still get a solution, right? I can tell you exactly what a factor of 2 is going to do to an impaired activation barrier. Depends on the temperature. At room temp, it's about 2 kilojoules per mole. But you could have gone about this either way, and you'd have been correct, as long as you clearly state your assumptions. I would have counted either of these as A-OK. Obviously, it's easier to do the second one because then E high is simply equal to what? Say it loud and proud. E1. Right? Because we've essentially made that 2 go away. So. But again, you could account for it, and it would be something like E1 minus some small number. But that would depend on temperature. And we don't know the temperature. So it would make the algebra much more difficult if we didn't throw away that 2. Okay, so that's one of them. So we've done this one. What do we need to do now? The low limit, right? So do we know anything about the low limit? Was anything given to us about the low temperature? This is where this problem gets tricky. Yeah.
Aren't we pretty much given that values are equal at T break, the temperature of the break?
At the break temperature that the values are equal. Yeah, you know that, but you don't know what that temperature is. And I asked you for the low limit. So I'm not sure that that's going to help you. But you've identified something that we know. What do we know? We know that there's a change, right? We know that there is a change. Okay, so if we went to low temperature and we got, again, that K2, that's what we had, right? Is much greater than K1 at both low and high temperatures, that's possible. Would we see a break in the linearity in that situation? No. So instead, then, we know that if we go to a low enough temperature, the reverse rate constant must be much larger than the forward for K2. And so if that happens, we cancel out this one, right? And so what do we get for K effective high, or excuse me, low? 2 times K1 times K2 over K minus 1? Yeah.
In regards to the graph, is it normally ln of K, not ln of long?
Yes, but I'll point out that that can be the same thing depending on, but yeah. Just remember that K is changing. So this goes back to the chapter we skipped, which is collection and analysis of rate data. Because this K that you have here is not the grouping of rate constants that you derive. It's something that you observe based on kinetic data. Does that make sense? But yeah, we kind of skipped that over, so you won't be expected to know how that happens. But essentially, you could, for instance, say that the rate was equal to just some power law. And so at each data point of rate that you got, you could define some K, which is automatically some effective K, because I've only put it in here once, is equal to the rate divided by the concentration to that power. But again, you're not going to be tested on that. We're going to talk about collection and analysis later. So coming back to here, is this pretty clear? So if we again make the assumption that this 2 can essentially be thrown away, then what is E low? Do I need to go through the trouble of putting all those things in the Arrhenius? Or is there some relationship between how rate constants multiply together, what happens to their activation barriers?
So it'd be like E1 plus E2 minus
Yeah. You just get the sum of the activation barriers out of a product of rate constants. Again, we're making the assumption here that this is, for all intents and purposes, same as that.
What do you do if there's like a plus or minus and you can't do the E? So it's like at the bottom of the...
Not algebraically, not analytically, no. So when you're in that regime where it's both. So the other thing that we knew, that's a good point, and we didn't, I heard hesitation and I wasn't sure why. Some of you guys seemed hesitant when I made this assumption. And it's for good reason. Why? I mean, at high temperature, this is true. And if this is true at high temperature, then we know that there's no break in the linearity. And we know that the problem said there's a break. Well, why does this have to be true then at low temperature?
Is it only so there's one
magnitude that you would end up with the exact same activation energy?
No.
So there's only one break. So it couldn't...
It's because there's only one break between two linear regions. So the problem statement told me that I get to a linear regime. That means this has to cancel out into something that looks like this. If I've got a plus, it's nonlinear. So that's kind of your question is, what do I do when there's a plus? Well, it's not going to be linear. And so if I'm told that there's two linear regions, I know that I have to make some sequence of assumptions in order to get rid of that plus. And again, that leaves me with one of two options. I can either say this is true or this is true. But if this was true at both low and high temperatures, there'd be no break in linearity. It's not an easy problem. So be happy it's today and not Tuesday. You might also notice that this is the same as big K1 times K2. And that might remind you that the difference between the forward and the reverse barrier for a reaction is what? The reaction energy. So keep in mind things like reaction coordinate diagrams, right? This is E reaction 1. This is E1. That's E minus 1. The difference, this minus this, is equal to that. Okay. What else? What else? What else? The rest of the problem. Right. All right. So we have E high and E low. And what else did the problem ask me? Yeah. So how do I define that?
minus E minus 1 is greater than or less than 0.
Okay, E2 minus E minus 1 has to have some relationship with 0. And do I know what that relationship is? Let's talk through it. So we knew that at high temperature, what was true in terms of these rate constants? K2 was much larger than K1. And at low temperature,
Negative.
it was the opposite.
Negative.
So if I know that those two things are true, what do I know about their relative activation energies? Greater than or less than? Everybody see that? Does everybody know why? So if I change with temperature, if I change the temperature, which rate constants move more? Large ones or small ones? Sorry, let me rephrase. If I change the temperature, will the rate constant for a large activation energy process move more or less than the rate constant for a small activation energy process? It will move more. The larger the activation energy, the more sensitive you are to temperature. And this is telling me that at some temperature way down here on the scale, 0 and infinity, K2 is some value, right? K2 and your K1. Do they both increase or decrease with temperature?